All right, this lesson is on implicit differentiation. So the main thing that we want to do here is, by the end of this lesson, is be able to find the derivative of a function that is defined implicitly rather than explicitly. And we're going to find out what those two terms mean, explicit and implicit functions. And along the way, we're going to talk a little bit about some notation that we use when we are talking about derivatives. So, um, the notation that we've been commonly using up until now is this function notation. F at x equals 3x squared plus 2, something like that. And then when we find the derivative, we just indicate with the little prime there, f primed is equal to 6x. We can also use a slightly different notation, what's called Leibniz notation. If we define our function as y equals 3x squared plus 2x, the derivative is indicated as dy dx is 6x. And the dy dx, the numerator means take the derivative of y and the denominator, the dx, means with respect to x. So the derivative of y with respect to x. Now, most of the functions that we deal with in this course, we don't have to specify that we want the derivative with respect to x because our variable is always x. But as we move on to some other applications, we might look at functions that have more than one variable in them. So for instance, let's say we were looking at a function like this. This would be an expression for volume of a cylinder, right? Volume is pi r squared h. And we wanted to take the derivative of this. We've got two potential variables in here, r or h. So we could take dv dr, i.e. the derivative of volume with respect to r, or the rate of change of volume with respect to radius, and that would give us 2 pi r h. Basically, we're just bringing down the 2, we're keeping the pi as a constant, and we're treating the h as a constant too, so it doesn't change our derivative. We could also treat h as our variable. We could find dv dh, or the rate of change of volume with respect to height. In that case, we would treat the pi as a constant, the r squared as a constant, and h is our variable, so we'd end up with pi r squared. Okay, and notice that these expressions we get for the derivatives have a relationship, like a geometric relationship, to what was going on in our cylinder. Right, the pi r squared is like the area of the base. The pi r squared h is the area of the curved side. Now, this becomes particularly interesting when we look at how we can apply the chain rule in this Leibniz notation. So let's say we've got a function that is defined as y equals f at g at x. Okay? And we want to find the derivative of y with respect to x. Okay? On our right-hand side, we're going to have two of these fractions, like the dy dx. We are first going to take the derivative of y with respect to f, and then we're going to multiply that by the derivative of f with respect to x. Oh, sorry, not f, sorry, g. Derivative of y with respect to d, g, and then the derivative of g with respect to x. Now, looking at this, this kind of looks like you're just sort of doing a sort of a unit conversion here where the dg's are going to cancel each other out. Why does this work in terms of our chain rule? Well, let's apply this for a specific function here. Let's say our function was y equals 3x plus 2 all squared. Okay, we want to think of this as, just change colors here, y equals sorry, we use g as our inner function. So let's think of this as y equals g squared, where g is 3x plus 2, right? So g is our function of x, and y is a function of g. If we're taking our derivative here, okay, our chain rule would be dy dx equals dy dg times dg dx. So dy dg means take the derivative of this function y, treating g as our variable. So we're going to bring down the 2, and we're going to have 2g, okay? Assuming that treating this as just y as a function of g. And then dg dx over here, we're going to have 3x squared. Derivative of that with respect to x is 3. Now, if g is equal to 3x plus 2, we can sub in 3x plus 2 for g, and we get our normal expression that we've seen when we've applied the chain rule in class. So this version of the chain rule here with the sort of the 2 with all of the d's in it here, it's called Leibniz notation, and we're going to use this a little bit when we answer certain questions involving related rates. Okay, on to the main part of the lesson here. Explicit and implicit functions. Okay, so we have been dealing with functions that are defined explicitly. Something like y equals 3x squared plus 2x is an explicit function, right? We've got x on one side, we've got y on the other side. It's y equals something in terms of x. Functions or relations can also be defined implicitly. An example of an implicit relation is something like this. X squared plus y squared equals 36. We recognize this as the equation of a circle, but notice that the x and the y we aren't expressing this as y equals in terms of x. The x and the y are kind of mixed together on one side of our equation here. Now, we could take something that is defined implicitly and we could turn it into an explicit function. Like we could take this and we could bring the x squareds over to the other side. And we could take the square root, remembering that we want to take both the positive and the negative roots. And we could express this as an explicit function. So I should actually kind of move this over here, right? So this is kind of going from here to here, and we could get this to be an explicit function. Okay, but in some cases, it's not very easy to take an implicit function, turn it into an explicit function, and then find the derivative of it. So what we want to be able to do is we want to be able to find the derivative of a function which is defined implicitly. How do we do that? There's this relatively simple process. The key thing that we have to remember is that when we are doing implicit differentiation, we have to treat all of the y terms as composite functions of x, or as functions of x. So if we have something like y cubed, and we want to take the derivative of it, we have to remember that that y that we see in there is actually a function of x. So we're going to have to use the chain rule when we're doing this derivative. We're going to bring down the 3, treat y as our inner function, so keeping the y exactly the same, and then multiply by the derivative of that inner function. Derivative of y with respect to x is dy dx. Okay? So let's say we've got something more complicated, like x squared minus 2y cubed plus 4y equals 2. We want to find the derivative of this function here. What we're going to do is differentiate both sides with respect to x. So we're going to take the derivative of all of these terms with respect to x. So If my first term here is x squared, derivative with respect to x is 2x. My next term, negative 2y cubed, I'm going to take the derivative with respect to x, remembering to treat this as a composite function. So I bring down the 3 to get 6y squared times dy dx. My next term, plus 4y, again, I'm going to take the derivative with respect to x, treating this as a composite function. 4, and the derivative of y is just going to be dy dx. And on the right-hand side, the derivative of 2 is just 0. Okay? What I'm trying to find here is an expression for the derivative. I want dy dx. So I'm going to move all the dy dx terms over to one side. So in this case, it looks like all I have to do is move the 2x to the other side. For dy dx is going to equal negative 2x. All right. And then I'm going to factor out this dy dx here. So dy dx is common to both of the terms on the left-hand side. Negative 6y squared plus 4 after I factor that out. And then I'm just going to solve for dy dx. So I'm going to divide both sides by that thing in brackets. Dy dx is equal to negative 2x divided by negative 6y squared plus 4. Okay. So I've got an expression here for my derivative. My derivative is dy dx, and it's expressed here in terms of both x and y. Okay. So let's look at a second example here that has a little bit of a trick in it. 2x to the power of 5 plus x to the power of 4 times y plus y to the power of 5. And again, we want to take the derivative of this thing. Okay? So this one, it would be really tricky to rearrange it and solve for y because this middle term here has x and y multiplied together. But let's go ahead and do our derivative implicitly. We're going to take the derivative of each term with respect to x. So bringing down the 5 gets us 10x to the power of 4 plus, when we do the derivative of this middle term, we have two terms multiplied by each other, x to the power of 4 times y. We have to remember to use the product rule. So 4x cubed y plus x to the power of 4, and the derivative of that y with respect to x is dy dx. Plus, again, we're going to treat this y term as a composite function, bring down the 5, subtract 1 from the exponent to get a power of 4, multiply by the derivative of the inner function, dy dx. And all of this is going to be equal to 0. Okay, now those brackets really aren't doing anything, but we want to get all of the terms that have dy dx on one side. So let's just pull everything else over to the right-hand side. So I'm going to keep x to the power of 4 dy dx plus 5y to the power of 4 dy dx on this side, negative 10x to the power of 4 minus 4x cubed y onto the right-hand side. I'm going to factor out the dy dx. Keeping everything else the same. And then I'm going to divide both sides by that expression in brackets to isolate for dy dx. So I'll have negative 10x to the power of 4 minus 4x cubed y divided by x to the power of 4 plus 5y to the power of 4. And that would be the expression for my derivative.